Okay, so we've been saying all along that part of the reason we want to have these minimal spanning sets is in order to put a coordinate system on your abstract vector space. Okay, so that's what we're going to do today. Coordinate systems. So let V be a vector space, and B be a basis. Okay. So we use capital B to denote the basis. Then, as we saw before, for each vector in your vector space, there is a unique expression. There's a unique expression of V as a linear combination of the B's, right? V is going to be, some alpha 1, B1, alpha 2, B2, plus alpha n, Bn. There's a unique expression, blah, of V as a linear combination of the BI's. And there's only one way to do that, right? There's only one way to do that because of the linear independence. Okay, we take all those coefficients, we take all those unique coefficients, and put them in a column vector, and call that thing the coordinate vector with respect to B, with respect to the basis B. Okay. So, and we'll denote this by V in brackets sub B. So the coordinate vector of V with respect to the B basis. And the point of the game is that it will sometimes be very useful to change your coordinate system. Right? The standard, right, you have your standard coordinate system, right? The standard coordinate system is this one, E1 is 1 0 0 0 0 blah blah blah. E2 is 1 0 1 0 blah blah blah. Right, up through En, and so that's a standard basis of Rn, say. But sometimes, it will be useful to not use the standard basis, and that will simplify matters considerably. Okay. Okay. So let me. I'm going to erase this. Is that all right? Everyone done copying this? Okay, so erase this, and we'll do an example that will sort of illustrate why it is useful. Markov chain application. Okay. So so here's a system. Okay. There's a place. It has a city. It has suburbs. Okay. Initially, 30% of the population is in the city. Okay. So it starts off 30% of the population is in the city, and every year, let's say at one point, like at the very beginning of the year, something happens. That is, 6% of those in the city leave and they go to the suburbs. 2% of those in the suburbs decide to go to the city. Okay. And you'd like to know what happens in the long run, say. Right. Does this reach some sort of equilibrium state, for example? Okay, so one can model this system in the following way. You say we're going to let V be CS, where C is the percent in the city, and S, 1 minus C, is the percent in the suburbs. Okay, so for us at the very beginning, we have 0.3, 0.7. This is called the state vector. Right? What's the state? What is the state of our system? Okay. And then you create this thing called the transition matrix. 0.94, 0.06, 0.02, 0.98, the so-called transition matrix. And you notice that we've designed it so that AV then turns into, right, you get 0.94C plus 0.02S, 0.06C plus 0.98S. Yeah, Charlie.
How did you get the values of 0.3 and 0.7?
That's from here.
Oh, okay.
Yeah, that's sort of given to you. The initials, for us, 30% start in the city. Yeah.
I didn't see.
That's okay. It's not that important. C and S, whatever they are. Okay. So, okay. So you see what the use of the transition matrix is, right? You notice that if I take the vector V and I hit it with the transition matrix, then I end up with 0.94C plus 0.02S, 0.06C plus 0.98S, right? And so, you know, the matrix hitting the vector with A is the same thing as 1 year passing. Right? It's the same thing as 1 year passing because, right, after, and this is the state vector in the next year, right? Because after 1 year, who's going to be in the city? Well, it'll be 0.94 of the original city population plus 0.02 of the former suburban population, right? Who's going to be in the suburbs? How many people are going to? What percentage is in the suburbs? Well, it'll be 0.98 times the current percentage, and then plus 0.6 of the city, 0.06 of the city, right? And so this matrix here models this, right? This behavior. Okay. So our question was, what happens after n years? If you take the limit, if you do this thing and let n go to infinity, and hit 0.3, 0.7 with that thing, it turns out to go to 0.25, 0.75. Okay. So that is, in the end, you end up with a quarter of the population will end up in the city. So it turns out that should be sort of unsatisfying to you. Like, it turns out. What do you mean it turns out? Okay, so let me ask a question. What if I take 0.25, 0.75, and I hit it with the matrix?
Can you read the question?
What happens to 0.25, 0.75 if I hit it with the matrix?
Shouldn't it be the same?
Is it the same thing? Yes, it is. Right? Yes, it is. Right? Why? Why?
Because that's like a state of equilibrium.
Right, right. So, basically you've just hit this thing with, you've just seen what happens to this thing as you hit it with a to the n as n goes to infinity, right? Hitting it with one more a isn't going to do anything, right? It's like adding, it's basically saying that I'm going to look at a to the n plus 1, right? Well, that's still going to be the same thing, right? Okay, so this vector is not affected by a. This vector is not affected by a. It's held stable. It's what's called a steady state vector. So. Okay. Okay, so this should be sort of mysterious to you, but it can be clarified. So the above can be clarified. The above behavior, say, can be clarified using a change of basis. So this is going to be a little bit mysterious, but bear with it for now. So allow us to magically choose two vectors. The first one, u1, is going to be 1, 3. The second one, u2, is going to be negative 1, 1. Okay. What's good about these vectors? If we look at a times u1, well, u1 is just 4 times the steady state vector. Right? U1 is just a multiple of the steady state vector, and so it itself is also a steady state vector. Right? It's not going to be affected. Right? So U1 doesn't get changed. U1 doesn't get changed. Okay. U2, if you calculate it, turns out to be U2 itself, again, but multiplied by some constant, 0.92. Okay, so now if we express, say, 0.3, 0.7 in terms of u1 and u2, we see that 0.3, 0.7. Actually, let me write this up here. we see that 0.3, 0.7, if you work it out, turns out to be 0.25 of U1 minus 0.05 of U2. Okay, and if you think about it in this way, then the behavior becomes clear. Then we notice that a to the n times 0.3, 0.7 if we take a to the n and hit this thing with it, well, what happens? Right. A to the n times 0.3, 0.7 is this, right? Well, this is going to be 0.25 a to the n u1 minus 0.05 a to the n u2. Okay, but what is this thing? A to the n times u1, what happens?
U1.
Come here, yes. So it's just going to be u1, right? Because u1 is not affected by a, right? So we get 0.25 times u1. And then what happens to this part? What happens to u2? Well, every time we hit u2 with a, what happens? Henry?
It's the 0.92.
I get 0.92 times u2, right? So this is going to be 0.05 times 0.92 to the n u2. Okay. And then as n goes to infinity, 0.3, well, you know, this is going to be 0, right? 0.92 to the n is going to go to 0, and so the second thing is not going to affect. And so we end up with 0.25 u1, that is to say, 0.25, 0.75. Okay. So the point here that the point of this example is sort of to say that it's better, instead of thinking of your vector, instead of thinking of things in terms of the standard basis, maybe it's better to think of them in terms of this u1, u2 basis, right? Because with respect to the u1, u2 basis, the behavior of A is very simple, right? With respect to the standard basis, the behavior of A is like this, right? With respect to the u1, u2 basis, the behavior is like this. A of u1 is u1, A of u2 is 0.92 u2, right? Right. So if you think, you know, what does A do to the to 1, 0, right? Well, it will give you 0.94, 0.06, right? A of E2 is 0.02, 0.98, right? So the behavior with respect, right? This is 0.94 of E1 plus 0.06 of E2. This one is 0.02 of E1 plus 0.98 of E2. Right? The point is that the behavior with respect to the standard basis is complicated, right? But with respect to this new basis is simple. And so maybe it's a good idea to switch your expressions all over into the new basis. Okay? Just to give you some terminology, these guys are called eigenvectors. Okay? Eigenvectors. So any vector which, when hit by eigenvectors of A, any vectors which, when hit by the matrix, only get scaled, right? They only get multiplied by some number. This guy is very nice, it gets multiplied by 1. This guy is, also pretty nice, it gets the only thing is it gets shrunken by A. These guys, E1 and E2, are not eigenvectors of A, right? As you see, when you hit E1, you don't get a copy of you don't get some multiple of E1, right? You get some combination of E1 and E2. Similarly for E2. Okay. So the moral is, it might be a good idea to switch over to a basis consisting of eigenvectors. Andrew first.
How do you choose U1 and U2? You just randomly pick?
Magically. For now, yeah, magically. Okay. But we'll see how shortly. But right now, so I'm not gonna tell you about how to get eigenvectors. It's easy, but I'm not gonna tell you right now. Okay. Yeah. Right now we're gonna talk about how to change the basis. Okay. Yeah, Chelsea.
That was my question.
Okay. Yeah. So for right now, it's just gonna be mysterious, but it's not that complicated.
I didn't understand the last step over here.
Right here.
Yeah.
Okay. So this is an applied to the initial state, and you see that turns into it's this thing, right? Okay. Now let n go to infinity,
Yeah.
right? As n goes to infinity, well, this isn't affected by n, right? This doesn't depend on n. This thing, on the other hand, will go to 0,
Oh, okay.
right? Because 0.92 to the n goes to 0, right? And so you end up with just this thing staying there. So the limit of this is going to be 0.25 times u1.
Okay.
Okay. So let's talk about change of coordinates. Okay. So in Rn. So first we'll do it in Rn, and next we'll do it for general abstract vector spaces. So let V V1 through Vn and V1 through Vn be bases of Rn. Okay, and suppose we know the coordinate vector of some vector x, so x is in Rn. Suppose we know this, right? That this is something like C1, C2, C3n. That is that x equals C1 V1 plus Cn Vn. And now I understand why in my text I was writing these things all as column vectors. So actually, let me write these guys all as column vectors. You don't have to, you may just write some note that these are all column vectors.
Are you multiplying those? What do you, right there?
Right here?
Yeah.
Yeah, right. So, right, this is what this should be like. In other words,
Oh.
so, right, so let x be some column vector here, and let's say that the coordinate vector of x with respect to b is this, right? So this is notation we just introduced maybe half an hour ago, so you may have forgotten it. But what this means is that x is this particular linear combination of the b's, right? X is expressible with respect to the b basis with these guys as the coefficients. Okay, in other words, x is c1 b1 plus blah 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 uniquely. Okay. Okay. Suppose we know that, and we'd like to know the expression of x with respect to the v basis. Okay, so you want to change your coordinates to the v basis. Okay, so what is it? Right. How do we get x with respect to the v basis? I'll let you think about it for a minute and see if you figure it out. It's not that hard. Just think about it. Anyone have an idea? Maybe it's a little bit tricky. So you think like this. You say, well, look. Well, x, right? X is this thing, right? C1 B1 plus C2 B2 up to Cn Bn, right? Which we're going to rewrite. We'll get it like this: B1 B2 Bn times the vector of C's, right? This thing is the vector C1 to Cn. Right? That's just a translation of this, right? Right. Okay. And so we're hoping to figure out how to express. We would like to know what this guy, right? We would like to know this guy. And so all we need to do is take the inverse function of this thing and multiply, take the inverse of this matrix and multiply on the left by it. Right? So to find the coordinate vector with respect to v, it's going to be just you take your coordinate vector with respect to v, multiply it on the left by the basis matrix for b, and then multiply by the inverse of the basis matrix for the b's. Okay, let me make this concrete. Okay, so it's a bit again. It looks complicated, but in fact, it's something very straightforward. Okay. So for example, we had this thing, 0.3.7, right? And this was with respect to the standard basis. And suppose we want to say we'd like to express this thing in terms of the u guys, right? Which was 1311, right? U1, 1, 3, and negative 1, 1, sorry. Okay, right, this was U1, and this was U2. Okay. Okay, so let's just follow the rules, right? Right. Let's call this right. So right, this 0.3.7 to make it look exactly like this. I'm going to say something kind of dumb, which is that 0.3.7 you think of as 1001 times 0.3.7. Okay, that looks kind of silly. All I'm saying is that we're using the standard basis here for our b's, right? So this is b1 and this is b2, right? This was the expression with respect to the standard basis. We don't really need to do this, but I'm just making it explicit. Okay. So then the expression with respect to get the expression of the thing with respect to the U matrix, with respect to the U basis, what do we need to do? We take the U vectors, 1, 3, negative 1, 1. We put them in a matrix. We invert that matrix, multiply by 1, 0, 0, 1, and 0.3.7. Right. So that's this thing here. Right. The coordinate vector. Oh no. The coordinate vector with respect to the v basis, with respect to the u basis, is going to be the matrix formed by taking the basis vectors, inverting that, and then multiplying that by this thing, right? So that's, you take your U matrix, you invert it, and you multiply by this thing, right? This is your, right? This is x with respect to the E guys. This is E1, E2. This is E1, E2. This is U1, U2 inverse. Right? That's here. That's this stuff here. Okay, and then you work it out, right? You multiply it out. You figure out what the inverse matrix is. Blah blah blah, and of course, it turns out to be 0.25, 0.05. Right, which is what we had. I stated it, and here's how you would calculate it. Okay. So this guy expressed in terms of U1 and U2 is 0.25 of U1 plus 0.05 of U2. Right? Okay. So anyway, the point is this, right? To get a matrix that takes you from one coordinate system to another, here's what you need to do. The matrix that takes you from the coordinate expression with respect to b to the coordinate vector with respect to x is exactly this matrix here, right? You take the b, you take the matrix of basis vectors from b, and you multiply it by the inverse of the matrix of vectors from basis vectors from v. Okay, so this is this thing here. This thing here is the change of basis vector, change of basis matrix from the B coordinates to the V coordinates, or B basis to the V basis. I think it's clear to call it coordinates. Okay. So here's an example. This one is from the book. They give you one basis, B, which is 5, 2, 7, 3. And they give you another basis, B prime, which is 3, 2, 1, 1. Okay. And they say, what's the change of basis guy from find the change of basis matrix from the first guy to the second guy, to the second basis. Okay. So write down what you need to do. Take half a minute and write down what you need to calculate. Don't do the calculation, it's not exciting. But just write down what you need to do. Okay, turn to somebody else and say what you did. Yeah, it should begin with you just. I hear a lot of people saying you just. In fact, it's you just. Okay, so what is it? Yeah, so somebody just say it, blurt it out. What is it? What's a matrix?
It's just B prime inverse.
It's just what?
B prime inverse.
What do you mean B prime inverse?
So the inverse of 3, 2, 1, 1.
Okay, 3, 2, 1, 1 inverse.
Times B, so that's 5, 2, 7, 3.
Okay, yeah. So it's a little bit imprecise to say B prime inverse because B prime is a basis, right? And you don't really say B prime, but you don't say the inverse of a basis, right? Right. So if you wrote on your exam B prime inverse times B, I would say like what? Yeah. Yeah, I wish, there are all sorts of things that I wish I had as stamps, like nonsense. That would probably be the most useful one. But I don't have anything like that. Yeah. Instead, I have something that says I have this thing that I got in Japan that says yoku dekimashita. Taihen yoku dekimashita, which means you did really well, or yoku dekimashita, you did pretty well. Ishoni ganbarimashou. Let's all work hard together. Okay. So that's so this is pretty straightforward, right? Going from one basis to another, blah blah blah. You just do this. Okay. So let's move on to the more complicated thing, which is the case of abstract vectors. Okay, so abstract vector spaces. So it's sort of the same setup, but a little bit. It turns out to be a little bit trickier. So. Be a vector space, and you have a basis So these guys are not column vectors. These are, just some vectors in the abstract vector space. Okay. Given a vector in the vector space, as usual, we define, just as before, we define the coordinate vector with respect to the basis, coordinate vector of V with respect to E as C1 through Cn, right, in Rn, where V is C1 V1 plus Cn Vn, where this is the unique expression of V in terms of as a linear combination of the VI. Okay, so you notice what this gives you. You have an abstract vector space, and then for everybody, oh wait, hold on. You have an abstract vector space, and then this gives you, for each vector in your vector space, a corresponding vector in Rn, a unique corresponding vector in Rn. Okay, so you could think of this as a kind of map, right? This is a map from your vector space into Rn, a well-defined map, right? And it takes, if you start out with different guys, you end up with different guys here, right? No two different vectors are going to end up with the same thing here. Okay. So just to give you one example, if we are in P3, remember the polynomials of degree less than 3, and you have some basis. The basis being, say, 1, 2x. 4x squared minus 2. Then x squared with respect to the b basis is a half, 0, a quarter. Right? If you take a half of the first guy, nothing of the second guy, and a fourth of the last guy, you see that you end up with x squared. Right? So this is the coordinate vector of x squared with respect to the b basis. You can work that out, by using linear algebra, using some matrices. I'm not going to talk about it. It's easy. What's not easy is the change of basis. Okay. So change of basis for abstract vector spaces.